Hello everyone. In this video, we're going to go ahead and introduce the notion of linear systems of equations. So we're going to start with a motivating example, and nothing motivates like baked goods, so our example is going to involve baked goods. All right, so we're going to have a word problem here. So suppose we want to buy a box of baked goods, so we're allowed to put in 24 total, and we get to choose from 3 choices. So we can put either cookies, scones, or muffins, and we can combine them. We know that cookies cost $1, scones are $2 per scone, and muffins are $1.50 per. You have $31 as your budget. And since you're a big fan of cookies, because let's face it, we're not sharing this with anyone, because why would we? So you want twice as many cookies as scones and muffins combined. And so we want to know how many of each are we choosing to put in the box. So this is actually a linear algebra problem. So we can associate to this a system of linear equations. So we should give variables, right? So we can just do, C equals number of cookies, and similar for the other two. So now, how do we start turning this into some algebra, right? So how do we put this in more math terms? So we have kind of 3 constraints here, right? So the first is that there are 24 items. So we know that C plus S plus M is going to be 24, right? And I'll just call that number 1. Second, we have the prices and we have our budget, right? So you can kind of think of this as a weighted sum, right? So C, or 1 times C for the dollars, plus 2S, because scones are $2 a piece, plus 1.5 M, muffins are $1.50, is equal to 31, right? We can use all of our budget. And then finally, we know we like cookies. Who doesn't? And so we want twice as many of these as the others combined. So how do we write that? Well, that means our cookies, this is 2 times twice as many as the others combined. So that's just going to be the sum of the other 2. Okay? So then the question is, how do we solve this, right? How do we actually find what C, S, and M are that satisfy all 3 equations simultaneously? So there are a lot of different ways to do this. One that jumps out at me right away is IC and S plus M. IC and S plus M, I can substitute, right? So from 1, S plus M is 24 minus C. So plug into 3. And we get C is equal to 2 times 24 minus C, in which case we get C is 48 minus 2C, 3C is 48, so C is 16. All right, great. So then simplify, right? And then 1 is then going to become, we kind of get a new system, right? So knowing that C is 16, S plus M has to be 8, right? We just subtract 16 from each side in 1. And in 2, we can also substitute. And we just get 2S plus 1.5M is 15, right? We'll subtract 16 over to get rid of the C. And so now we're down into, instead of 3 equations, 3 unknowns, 2 equations and 2 unknowns. And from here, again, you could substitute in some way, right? So from 1, whichever one is easier, probably S here. So S is 8 minus M. In 2 then, once we plug that in, we get 2 times 8 minus M plus 1.5 M is 15. Well, that's 16 minus 0.5 M, right? Minus 2 plus 1.5 is 15. Or 1 is 0.5 M. M is 2. And S then has to be 6. Right, and so we have exactly our 3 things. So this worked out pretty nicely, but we are going to soon in class go over kind of a more algorithmic method that will give us a consistent way to solve these things. So for your first exercise, now that we've gone through another system of linear equations and kind of solved it through, I want you to do number 3 from the worksheet from class. All right, so thus far, we've kind of done a few examples and kind of working naively through these things that I'm calling systems of linear equations, let's go ahead and actually get some definitions down and talk about these with a bit more context. So first, a linear equation in variables is exactly of this form. So I'll break down the pieces here. So underlined in red, our AI, these are real numbers, so that's what this means. So the epsilon means is in, and the R, this blackboard R, is the real numbers. These are just good things to know kind of going forward. So these are our coefficients, okay? And then underlined in blue, our xi are the variables. And then, of course, what makes this an equation is the equals d part. And so the d is also just another real number, right? So you've already seen these, right? X plus 3y equals 7, right? This is a linear equation in two variables, for instance. Now, you might be interested in what is a non-example, right? What is not a linear equation? So one of the key things to look at is with all of these variables, they are to the power 1. So basically what makes something not linear is, I guess, not being of this form, but in particular, a lot of times, you might see something like 3x1 squared plus 2x2 equals 4 or something. Basically, this 2 here is bad, right? This would be quadratic, not linear. Something else that would be kind of weird, if you had like a trig function or an exponential function or something, those also would not be linear. Okay, so this sine, bad. Okay, so not going to be a linear equation. A system, then, of linear equations is a collection of one or more of these equations in the same set of variables. Right, so, if you had like x1, x2, and then, y1 and y2, well, the x's and y's are different. So like, yeah, it's two equations, but not in the same set of variables. One thing that you might be worried about is if you saw something like 3x1 plus x2 equals 4, and then say x1 equals 6. Like, is this a system? Because it seems like they have a different set of variables. It is because they share the x1, and then you can think of the x2 as having coefficient 0 here. Okay, so if you see something that's just like missing, but then all the others are the same, you can just think of it this way and just deal with them by kind of filling in the coefficient 0. Okay. So if you notice with the very first example, we had 3 variables. And in general, if you had something, for instance, like x1 plus x2 plus x3 equals 0 or something, this does not give you a line. If you graph this, this is actually going to give you a plane in 3-dimensional space. Okay, and a plane is not a line. So why is it called linear? Well, the idea is basically if you have 1 or 2 variables, then you will get a line. And so we're just looking at more variables as kind of generalizing these cases with lines, and we just kind of kept the name linear. Okay. So just a quick example, right? If you just have one thing like this, x1 equals 3, or like x equals 3, right? This gives you a vertical line. And then if you had 2 variables, right, like x1 plus x2 equals 2, well, you're more likely to think of it, just because we tend to do this, is like x plus y equals 2. And so this is exactly like y equals 2 minus x, right? So this is a slope -1 line with intercept at y equals 2, okay? All right, so we know these have to deal with lines in general if they're 2 variables. So now we're going to look specifically at the geometry behind 2x2 systems. So in general, if you see m by n system, then the first coordinate is talking about number of equations. And the second is talking about number of variables. So here, obviously, it doesn't really matter because they're both 2, but in general, that's what we will mean. And so if you have, well, let's just do an example, right? So 2 equations, let's go with 2x minus 4y is equal to 8, and y is equal to 4x plus 5. So we have 2 equations, we have 2 variables. So hopefully you can see that both of these guys then are going to be lines. So the second one, that should be pretty clear. It's already in slope-intercept form. The first one, you'd want to kind of get it in that form if you wanted to graph it, for instance. So you could add over the 4y. So 4y is 2x minus 8 and thus y is 0.5x minus 2. And so there are two ways to do this, right? So like one, you could literally just solve this graphically. I'm not going to finish this out, but I'll at least kind of draw the start. So y equals 4x plus 5 is going to, maybe start up here, and it's kind of steep, positive slope. And then the other one is y equals 0.5x minus 2, so it kind of starts down here and has, again, positive slope, but much flatter. And so it looks something like this. So what's a solution? A solution is something that satisfies both. It has to lie on both lines simultaneously. That is this point, the point of intersection, right? So how do we find this point? I mean, you could probably pinpoint it graphically, or you can solve it like we did earlier, right? You could use, for instance, substitution. So y is 4x plus 5. That makes life pretty easy. So we get 2x minus 4 times 4x plus 5 equals 8. And if you go ahead and do this out, so it's 2x minus 16x, you get negative 14x minus 20, added over is 28. And so x is negative 2. And if you plug that in, right, it's negative 8 plus 5, and thus y is negative 3. And so this is the point negative 2, negative 3, and that is your solution. Can we generalize this? Like, what's going on? What do solution sets look like in general? So if we have two lines, right, 2 by 2 system is going to give us two lines in the plane. And then the solutions to the system are exactly the intersections or intersection points of the lines. So what can intersections of two lines look like? Well, we just saw one, right? So we just saw that like one can look like this and one can look like this, and boom, they intersect in one point. What else can happen? Well, you can definitely have lines with the same slope, right? You can have parallel lines. These guys are just going to go off forever and never touch, right? So this would be like 0 solutions here. They're parallel. This would have one solution. They intersect. One solution. And then, of course, you could have something that has infinitely many. And this is something we saw in class, right, where we only had one equation. And so we just had one line. And you could think of it even as like one line where one is on top of the other. So just a very quick example of this would be like y equals 2x and 2y equals 4x. These are the exact same line, just written in two different ways. And so this would be an infinite number of solutions. Is there anything else that's possible? Well, these are lines, right? So there's no way if they intersect somewhere that it like loops back around and intersects somewhere else. So this actually is it. So you either have 0, 1, or infinitely many solutions. All right, and for your second exercise then, I just want you to complete number 4 from the worksheet from class. And that'll talk about geometric solutions to 2 by 2 systems and get some practice with that. And then next class, we'll talk about actually solving algorithmically systems of linear equations. Okay, thanks for listening.